It's really fantastic to be here at YOW today, and thank you so much for coming and surviving until the very last session. I know I am standing in between you and the reception, so I'll try to make this as engaging and as fun as possible. So yeah, and hopefully with lots of food for thought, or then you could just drown your sorrows at the end. Now, I did go onto Amazon Prime, and I wanted to order a cannon that would shoot out Tim Tams to keep you all awake. And also, I'm from the UK. In the UK, we don't have Tim Tams unless you import them here from Australia. We have what's called a penguin, which is definitely not as nice. Tim Tams are infinitely 100 times better. So that is one of the many things you Australians get right, and we get fundamentally wrong in the UK. But unfortunately, it won't arrive in time here in Brisbane, so you're going to have to survive with this AI-generated image. Now, when I ask people about their experience of running large-scale systems, joy is very much on the bottom of the list of the word that comes to mind. You know, you're probably thinking about anxiety, pressure, being on call. How many folks are typically on call in their organization here? Yeah, quite a few hands. Anyone who's on call today? Oh, I see a few hands. So yeah, if the PagerDuty sound goes off, then we can all have that sigh of pressure. That one where the alarm and the pager goes off. We've sort of normalized running hundreds, if not thousands, of instances and lots of different systems with varying degrees of complexity under the guise of scale, and with the ever-increasing likelihood of failure within our particular systems. But it doesn't need to be this way. We need to reframe our understanding and our relationship with hardware and software to run systems more efficiently. Now, I'm going to start with my conclusion. So if you wish to run away, then I'm going to do a quick 360, and you could quickly make an escape for the door. I believe many systems of today don't take full advantage of the hardware that is available to them. Sometimes this is by design. Many of our learnings have come from a world where hardware had different trade-offs. Fear not, though, we're all practitioners in this room, and this talk will go into how that's been the case, sort of semi-accidentally, and evolutions in the industry that we can get excited about that take advantage of the hardware of today. Now, we're going to talk about a whole bunch of systems and software and design patterns and things that are going to sound new and novel and often associated with complexity. But I also subscribe to the Boring Technology Club. If you're a small organization or if you're just getting started, then you don't need to go write all of your systems in Rust unless you're writing something which is running at high frequency. You can get your cloud provider to run your software for you for a couple $100 and take advantage of all of the systems that they've built with all of their learnings. Oh. I should not touch the mic. Sorry about that. Think of this as more of a retrospective when it comes to engineering, and maybe a bit of a discussion about where systems are heading, especially when you're running at scale. Before we dive too deep, a quick introduction. My name is Suhail. Nice to meet you. And I'm a staff engineer at a company called Monzo. We are a bank in the UK, and I work in the platform group where we provide all of the underlying infrastructure so that engineers can focus on building a bank and not have to worry about whether their databases are up and running and whether their queues are continuing to be consumed and all the things like that. If you have used Heroku in the past, that's the kind of experience that we aim to emulate, but with sufficient guardrails and a very fast paved road. If you were in Gregor's talk a little bit earlier, he talked about really high guardrails and a paved road that's made full of sand. That's the experience that we try to avoid. We want a super fast autobahn, with the minimal amount of guardrails that makes the regulators happy. Now, Monzo is a consumer-facing retail bank in the UK, and we're also available in the US. We don't have any physical branches. Funnily enough, we actually have an API that we're legally mandated to provide, which is an API that lists all of our branches, and it's the most reliable API that we have because it just returns an empty list. And that hasn't changed in the 8 years that we've been operating. We power all of our banking features through an online app. We're a bit like Mi Bank here in Australia, I believe, but I argue that we have much, much nicer looking cards and potentially even a better app. So if any of you Australians want to be inspired about what banking looks like in the UK, please come and have a chat with me outside. Now, our whole philosophy at Monzo is to build infrastructure using composable microservices. We are a consumer-facing retail bank with direct integrations with payment networks like MasterCard, and we have a thing in the UK called the Faster Payment Scheme, which allows us to send money to our peers directly and instantly. And where there's many microservices that get involved, for example, when you tap your card to make a card payment. This includes things like recording the payment in our banking ledger, managing accounts, making sure that that is a valid payment, doing financial crime checks to make sure that a payment is all legitimate and you have the money available in your account and it is deducted accordingly. Now, all these interactions need to talk to databases and queues and other distributed systems, and we need them to be quick and mega reliable. We only have a handful of seconds from the moment that you tap your card to the point that we actually need to give a decision on whether we accept that payment or not. Ultimately, we don't want you to go to Bunnings and wait for your sausage sizzle. By the way, any Australians, if you could explain to me what a Bunnings is and why a hardware store sells food, that would be much appreciated. Is it like an IKEA situation? Yeah, please do catch me afterwards and let me know. Now, before I jump into the next few slides, in 2012, there was a publication on latency numbers that programmers should know. And I put some of the numbers on the screen here, and we'll revisit these in just a bit to see how things have changed. Now, keep in mind, for example, the last number there, which is the cost of a disk seek. Now, it's a little bit old and more geared towards spinning hard drives, but it's still important now to reframe how hardware has changed just within the last decade. Now, let's go into why all of this matters. If you've been part of a computer science course or cracked open an algorithms book, you will have come across a B tree. It's used in many popular database implementations, and B trees are fairly fundamental. They're used as index implementations in many popular databases. If you ever define an index using the create index command, it will almost certainly be implemented as a B tree when represented in your database system and on disk. Now, if you're familiar with a binary tree, it's a popular algorithm that you have. A B tree is very similar, where you've got a tree of sorted elements, and you can traverse the tree in order. And doing a search in a B tree is like doing a binary search in a large list. You start at the head, you make your way down to the node you're trying to find, and you can find any record in this tree that I put on the screen, for example, in a maximum of 4 comparisons, which is pretty good going. Now, B trees are self-balancing as you insert things, and they will juggle items around to maintain an optimum distribution. And many implementations will try and keep the height, which is the number of connections from top to bottom, as minimal as possible because it can affect performance. Now, why is this the case? These B trees are a data structure that lives on the hard drive, as opposed to, for example, being on RAM. There is a little bit of an asterisk because many systems have very large amounts of RAM, but let's assume that we're running on a constrained system. You're going to have to swap out to disk. This allows the B tree to grow as your data grows without the fear of running out of main memory. However, if your data is written over time, your B tree isn't going to live in a contiguous place on the hard drive. And you don't want your B tree to be splattered all over your hard drive. But that's what you end up with as your B tree grows and elements change organically over time. This means if you need to do a change or a lookup in your B tree, if you remember, for example, our search example, we had a tree with a height of 4. You need to do 4 comparisons. And what you're doing is you're waiting for that read-write head to continuously move around on the hard drive to get to the right position on disk where that particular bit might be located. And that's a couple milliseconds right there each time the read-write head has to move. When you're compounding all of those operations, that's tens of milliseconds just to do a single lookup. Even on cloud network storage like EBS, which may be much more familiar nowadays, you need to do 4 or 5 independent I/O operations, or IOPS, to do what an optimized system might do in a single I/O operation. Now, I'm not sure whether the vast majority of this audience remembers the days of having to do disk defragmentation. The general principle was that your data was splattered all over this hard drive, and it grew organically over time. And the idea of disk defragmentation was to lay out your data in a much more contiguous manner, to rewrite the empty slots on your hard drive and rewrite data points within your hard drive to maintain some amount of data locality, so that when you read data, the read-write head would need to move as minimally as possible. It's why defragmenting your hard drive made your computer feel much, much faster. Your files would be relayed out in a manner which made it much more optimized for how it would be read. Now, even in the age of solid-state hard drives, SSDs are much more efficient in reading sequential data rather than doing random access. Now, the above chart is from 2009, but the premise of optimizing for reads and writes very much exists today because sequential is much faster than random access. On many SSDs, you can read 1 kilobyte or sometimes even 4 kilobytes of data in a single I/O operation, and that means your system can be much faster if your data is fully local and fits within that 4 kilobyte page. If your bytes are scattered all over the place, then you have a whole bunch of seek operations before you even manage to read 4 kilobytes, ultimately reducing the performance of your application or like a database, queue, whatever you want to call it. Now, when a lot of the algorithms for many modern systems that we run today were designed, we had a completely different set of trade-offs. To read an item from disk, we were talking milliseconds. With SSDs, that has reduced by an order of magnitude to sub-millisecond. And now with NVMe SSDs, that has gone down to nanoseconds. And again, with throughput, a hard drive would saturate at about 200-ish megabytes per second. And nowadays with NVMe, you can breeze past that multiple gigabytes a second. I saw an NVMe drive a couple months back that could reach over 7 gigabytes per second. And some of these drives are getting wickedly quick. They are generating so much heat that you need to add a heat sink on top of these drives just to keep them cool because of the speeds that we're utilizing these chips at. And all of this is fine and dandy. Many of these improvements we can get without any changes in our application at all. For example, you can get some benefits of added CPU or better network headroom or faster disk speeds by deploying existing applications on newer hardware. This is a chart from a Samsung white paper showcasing a higher transaction count per second for a MySQL benchmarking workload using the exact same hardware but with different types of disks. So SAS disks versus NVMe versus SATA disks and things like that. This might sound a little bit contradictory to the B-tree example that I gave a couple slides back because clearly, just changing the hardware is significantly increasing our throughput. So there might be nothing that we need to do apart from just add more hardware. But with some small tweaks in the software that we write, this can accelerate off the charts and make it take full advantage of the speed. There was a really interesting research article that I came across a couple months back on further improving I/O performance by translating random write calls into sequential write calls at the block device layer. Now, this helps reduce wear on the NVMe drives itself. And in their benchmarking, they achieved a 5 to 11% increase in write transaction throughput, depending on the file system that was used. So, for example, in this particular test, they were using ext4, which is pretty popular, if you're installing many modern operating systems. So, 11% improvement is pretty neat. And, a lot of people would just take that. It's pretty great. Now, shifting from the world of hard disks, even in the world of CPUs, we've continued to see 10 to 15% year-on-year gains in single-thread CPU performance. Now, we're not living Moore's Law. We haven't been doing that for a couple of decades. But cumulatively, we're able to extract significant performance just out of a single thread. We don't even need to go into multi-core architectures. And these CPUs are getting ever larger. We can get CPUs with up to 48 cores with the Threadrippers nowadays. It's not about CPU frequency either. The caches on the CPUs themselves have been getting larger and larger too. Now, I've plotted the difference between L1 and L2 caches for different types of AWS instances. So these are instances that are in the cloud that run on the AWS platform. And you can see how there has been a continuous increase over time. Now, the leap may not look that dramatic when you look at the bars themselves. But overall, in software, increasing the probability of a cache hit can dramatically reduce the amount of CPU cycles spent. An L1 cache hit, remember, is 200 times more faster than going to main memory. For a long amount of time, our focus has been on x86-based processors. And now many providers are providing their own custom hardware, custom silicon, with ARM-based CPU processors at price points which are much below their x86 equivalents, often with similar performance, or if not better performance. AWS, for example, very recently announced their Graviton 4 chips, which have over 500 gigabytes a second of memory bandwidth across 96 CPU cores, which is pretty massive. There was a study done by the folks at Honeycomb where they write a bunch of telemetry software, and they reported a 30% improvement in price to performance of their server fleet using Graviton instances. So all they did was swap out their existing software onto different style of hardware with Graviton from x86 to Graviton, and had a 30% improvement in price to performance. And all they had to do to leverage these new types of instances was to retool their CI to generate build artifacts for ARM instead of x86 to take advantage of the hardware. And typically in many modern programming languages like Go, you can do that with a single environment variable, and it will just work. Now, there has been one principle of distributed systems that has held true over the years and may probably never change, which is the network has not gotten any more reliable in general, unless maybe you are the Google Cloud Spanner team, in which case you say the network is fully reliable. If you're building a system that spans over multiple machines and they need to do coordination, there's still a heap of work that you need to do in your application in order to handle network disruptions. But networks are getting significantly faster. In our original latency numbers, it assumed a 1 gigabit network, which was entirely reasonable a decade ago. But many of the major cloud providers now give you 10 or 25 gigabit per second networking nowadays, even on the bog standard generation of instances, so even on the cheapest fleet. A lot of networking behind the scenes is focused on hardware offload and bypassing the traditional operating system stack through things like XDP, because CPUs can't keep up with this super fast networking speeds. You don't have time to dawdle if you're processing tens of millions of packets a second. But there is one fallacy that has remained true, which is you still need to be aware of the pesky cloud egress charges. I think we have someone from the audience from AWS. If you could reduce our egress bill, that would be absolutely fantastic. AWS and the folks of like AWS and GCP are pretty happy to bill you 10 times as much with 10 times as much network performance. Oh, I think I'm going to stop moving my arms because that's going to cause a bit of feedback. But yeah. This is a Google Tensor Processing Unit, or a TPU. And there's a whole bunch of custom silicon which is purpose developed for machine learning use cases. And a key element of this particular hardware is all the fantastic designed CPU cores, the processing cores that are available for training, but also the network interconnect fabric that is available to these tensor processing units, which can sustain 10 terabits per second when clustered together for really fast distributed workloads. So if you're doing a lot of machine learning or like AI or LLMs and stuff like that, you can spread your workloads across multiple TPUs with terabits of bandwidth in between. So coming back to our latency numbers, our L1 and L2 caches have become much larger, and the likelihood of getting a cache hit and skipping main memory has also gotten much larger. We didn't get a chance to deep dive into main memory, but we're seeing successive iterations of the spec, and now we're on DDR5, which brings 3 to 4 times higher throughput and bandwidth. And this is especially important for multi-core systems. Memory is also getting significantly larger. You can get machines with terabytes of memory nowadays. You can fit your entire data set in memory for many applications, negating the need to go onto disk in the first place. Hard drives have also gotten significantly quicker, removing a really large source of bottleneck if you need to read something off disk. In 2005, there was an article titled "The Free Lunch is Over" by a bloke called Herb Sutter. And the article talked about the slowing down of Moore's law and how the drastic increases in CPU clock speed were coming to an end. Now, I was a little bit too young to understand this article, but when you read it in retrospect, it makes a lot of sense. It was almost like a crystal ball into the present of today. Now, take a second to digest that quote there. No matter how fast processors get, software consistently finds new ways to eat up all of that extra speed. Make a CPU 10 times as fast, and software will find 10 times as much things to do. Now, between that article in 2005 and the present day, we've had a big revolution in the era of cloud computing and a consumption-based rental model for hardware. Gone are the days where, you had to justify to your financial controller or whatever that you needed to spend 10 million buying new servers when you just spent 10 million the month before because you needed to run your applications at scale. We can now scale for pennies just by clicking a few buttons in the AWS console, and the fantastic AWS billing engine is happy to bill you ad infinitum for it. But that means that our software hasn't, been iterated on. We've not got a ton of regard for performance per unit of compute that we're achieving. Herb predicted that the next frontier will be in optimizing software. And at that time, that frontier was, declared to be concurrency. We'd be, all concurrency engineers. Today, we're all prompt engineers in this room. But we'd be concurrency engineers. Engineers had managed to grok objects and object-oriented programming, and concurrency was what we needed to become natural at. So Herb's thesis was all about, becoming much more proficient around efficiency and performance optimization to identify places where we could take advantage of concurrency. Herb predicted that languages and paradigms that lead to heavy optimization would find new life. And I think in today's era of software, that realization is more true than ever. Cumulatively, we use 1% of worldwide power on data centers. Now, you may argue that 1% is not a significant amount compared to other industries, and when you look at it in comparison to the monetary and societal value that computers create, it might not be that much. But our demand for compute is ever increasing, and I don't think anyone in this room would want to be wasteful. There was a really fascinating Intel report, and I found it particularly fascinating because Intel wins out as they sell more chips. So it's really fascinating that this report came from Intel that I read a couple months back, which stated that 50% of greenhouse gases are due to infrastructure and software inefficiency in the data center. Now, 50%, that figure on the outset seems really, really high. But when you think about the software that runs at your organization, or if you're a consultant, you go into many organizations, and you see software that is being run, when you account for provisioning buffers and runtime overheads and operating system overheads and just bad algorithms and virtualization overheads, that inefficiency does accumulate. And you can see how that 50% can come about. Hardware has gone on a lot faster and is giving us much more throughput in pretty much all aspects. And yet with the systems that we're running, we're still scaling into the thousands of instances. What is happening in the world of software that is taking advantage of all of those optimizations? Most of our multi-threaded applications nowadays follow a shared everything architecture. We have all of our data in memory, and we work on different parts of the same shared address space at the same time. Naturally, if two cores want to access the same parts of data, for example, let's say that a request comes in and you're writing to a bit of data with another request coming in at the same time that wants to read the same data, what you put behind it is a mutex to make sure that the two don't collide. You need to use a synchronization primitive like a mutex to guard against that particular race condition. Now, with a thread per core design, your application is pinned to a particular CPU thread, and you shard your data space so that each core is handling a particular portion of that particular data space. Now, this pattern hasn't become really ubiquitous in the software that we write today. And when I introduce this concept to many engineers, it's the first time that they're hearing about it, because it requires a bit of effort. Your application needs to become aware of the sharded space. And also, you have to have some element of request steering so that two requests for the same data space land on the same core. Now, you could run all of these requests in serial, but by using this sort of architecture, you can get rid of the synchronization primitives while still allowing for elements of concurrency within your system. What that means overall is that you can reduce the number of CPU context switches that your application needs to do, because that thread is only working on that particular data space within your particular application. Now, it's not only about data though. CPUs also need to context switch to handle things like network interrupts and disk interrupts and other kinds of I/O interrupts. As network packets come in, for example, the packet processing will be widespread across your CPU cores, which means if they are also serving application requests for data, your latencies are going to suffer. In Linux, for example, you can use pretty ingrained systems like IRQ to pin network requests to particular cores. But that also means that your application needs to be designed in such a way to leave that particular thread as a network handling thread to maximize efficiency. Now, there was a paper in 2019 that measured the impact on tail latency by pinning the network interrupts in popular open source systems like Memcache and Sphinx to particular CPU cores using IRQ. And they found a 71% reduction in tail latencies. Utilizing IRQ is not complicated. You can read the man page. It's relatively easy. There's plenty of blog posts out there as well. This model of computing isn't very revolutionary. Systems like Nginx have been doing this for absolutely ages and with really great benefit. However, this style of programming can be quite fiddly, as you need to get quite deep into the networking stack and build a model for thread-based message passing. Fortunately, there's some fantastic work in the open source world that can help you here. If you're a C++ user, definitely check out the C* framework, which I have linked there, by the folks at ScyllaDB. And I think there is also an equivalent in Rust and some other programming languages. They have a very comprehensive tutorial on how to get started, even if you are a novice to multi-threaded C++, like I am. In the world of asynchronous I/O, asynchronous I/O in Linux has been pretty complicated as well. You can get into a world where you'd implement asynchronous I/O in your application, but for example, your buffers would get full, or the I/O wasn't quite matching what your particular disk was doing, or the file system was expecting, or you'd filled your disk request queue, which meant that asynchronous call that you were doing became synchronous and blocking. There was a lot of memory overhead too with asynchronous I/O. So if you were doing lots of small requests, that overhead accumulated really, really rapidly. IOUring, for example, provides a new interface and APIs at the kernel level for Linux-based systems, which addresses these problems. And IOUring is not that complicated in its nature. It is two ring buffers. You submit your request in the submission queue, and then you can fetch the result in the completion queue. Now, here are two charts of random reads and writes for a 4 kilobyte block size with and without IOUring. Now, remember, towards the beginning of the talk, I was talking about random reads in the context of B trees. This is where it sort of comes full circle. If we were using the standard Linux async I/O operations, there's a cap on the number of operations that we can achieve before all of our resources are starved waiting for disk. That chart on the bottom there shows a massive delta on random reads with IOUring. It's a significant improvement. It unlocks a significant amount of performance and again questions the notion around disks and hardware being the bottleneck. For a long amount of time we've said, hardware hasn't kept up with the world of software. These benchmarks were done on exactly the same system. The only thing that we've changed is the software implementation that we're using underneath. Over the last couple of months, a popular open source library, libuv, added async I/O support. And I love the particular comment that the maintainer put, which is performance looks great. An 8x increase in throughput has been observed. Now, it's always important to be wary about benchmarks and synthetic workloads and stuff like that. But this is a multiplier benefit in a core library that is used across many systems. And anything that depends on libuv, in for example like Node and things like that, will get an immediate benefit in their I/O operations. So this is work that is happening right now in the community. Moving away from specific features and into the world of programming languages. Programming languages have also seen rapid development. To really take advantage of hardware that is closer to the metal, you usually had to resort to writing C or C++, which is difficult, error-prone. I've had my fair share of, failures and exceptions. And with the extremely rapid rise of system programming languages like Rust and Zig, that is a much, much, much better experience. It's a much better developer experience. And they're continuing to become safer and more delightful. The barrier to entry for programmers like me is becoming much lower. If you have the opportunity, I would strongly encourage you to have a go with Rust. I'm not a fanboy or anything, but I was amazed at how seamless it is to actually get started and even integrate with other existing programming languages like Python using libraries like the PyO3 bridge. I've worked with CPython quite extensively to write some stuff that was pretty slow in Python into C and call it from Python. But it's really, really difficult to get right and maintain and package. And the Rust ecosystem have, they've made it really, really simple with tools like maturing. The developer experience and the ergonomics are much, much better. There was some research in 2017 on the energy efficiency across programming languages. And they use the same data processing test suite with their implementation in different programming languages, and then rank the results for energy and time usage. Now, we're not here to start a programming language debate, especially for the last talk of the session, but it's interesting to see how different programming languages compare. Python, for example, is marked as being 75 times less efficient than C or Rust, and that is a massive, massive delta. Now, many moons ago, I used to work for a company that dealt with public transit data. Think like buses and trains and trams and things like that. And part of public transit data is dealing with schedules. And schedules have lots and lots of timestamps that we needed to parse and process and understand. Now, all of these in our interpretation were ISO 8601 timestamps. So we didn't have much variation to worry about. And what we saw is that in the hot path, this was taking a significant amount of time in the world of Python. And when we changed that out to a C-based function, that code saw an instant 10x speed up. And so this is how I got really interested in the space of software efficiency. It's quite a minor change. We introduced an open source library and changed the implementation, and we knew the types of timestamps that we were handling. And we saw a 10x improvement, which is absolutely massive. If you understand the constraints of your system, you can make assumptions rather than using generalized code out there that need to cater for every single permutation. Now, I wanted to get into the practice and actually see how easy would it be to actually translate the C library I was using to Rust. Now, if you are used to writing C libraries that interact with Python, there are a lot of footguns. You need to deal with PyObject all over the place and deal with the global interpreter log, and it is a big hassle. And then you've got to figure out your magic incantation with the make file and setup.py, and it's really, really a big pain. There is an open source library called Maturin, which provides a very nice UX for generating all of these bindings, and it generates a Python wheel, and it will give you a function where you can put your Rust code. So next few slides, we'll have just a little bit of code. You don't need to read and understand it all. We don't have time for a Rust 101. But effectively, what we have is I created a library called RISO 8601. It generated all of this code, and it gave me a parse datetime function where I could add our implementation. So this is what we need to do. You've got a string that looks like this. You need to extract out all of the components and convert it into a Python object. And we added our implementation to effectively parse all of these numbers. And one of the big benefits that we get for free is that even as part of this, you can raise exceptions within Rust, and they will get raised as Python exceptions. So for example, when we pass in a valid string, we get a valid Python object out. But when we pass in a bad timestamp, it's given us a very pretty exception, and all of this is handled by the bridge between PyO3, Rust, and Python. Maturin handles all of the packaging and building a wheel, and then you can put that out there, and it's really, really easy to use. It's really, really nice. Now, I'm not advocating that we stop what we're doing now and immediately switch all of our programming to using C or Rust or any of the new hot frameworks that are coming out there. If there is a takeaway, consider the inflection point where the runtime cost of compute power for your core or large systems has surpassed the development or organizational costs. Often we've optimized for the latter. We've optimized for organizational costs without any regard for refactoring or improving or profiling software, because squeezing out runtime performance was really complex. We called it premature optimization. But nowadays, abstractions have gotten a lot simpler. Hardware has changed quite significantly, and there is a big focus on the world of software with new frameworks and systems and tools to take advantage. Now, aside from hardware-related optimizations, there's been a big focus on wide-ranging improvements in programming ecosystems. In Java, for example, there's been a big focus on language features, but the one that I've been most excited about that has been released with Java 17, and now we have Java 21, which is also an LTS release, is the new ZGC garbage collector. I can't believe that I'm getting excited about a garbage collector, but it's really, really cool. Its goal is to give sub-millisecond max pause times regardless regardless of your heap size. Now, I enabled this for our Kafka clusters in production a couple months back and have been able to see these sub-millisecond pause times with my own eyes. It just completely reduces tail latency. So this isn't some distant reality. This is production ready today and being used by many organizations. For many of us that are programming or writing Java applications, for example, pause times, are a large contribution to tail latency and reduced throughput. It's ingrained in us, in the software that we write, that, we minimize the amount of garbage. But often we're operating systems and, large-scale systems like Cassandra or Kafka, where we don't want to go and change the underlying implementation. Some amount of garbage is going to be inevitable. So it's really exciting to see a world where we're, edging towards a pauseless Java. Now, I mention all of this because I know so many companies that are still running Java 8. There was a JetBrains survey a couple of days back that I think the number was 41%. Java 8 came out when the iPhone 6 came out. Think about that for a second. Even profiling your own software is really, really important. So for example, this is a workload that we have at Monzo. We have a Kafka cluster that's running, and alongside that Kafka cluster, we want observability. We want to know what is that Kafka cluster doing, what that Kafka is doing. So we run an open source exporter called the JMX Prometheus exporter, which is embedded as a Java agent. Now, I was doing a bit of profiling on our Kafka cluster, and I noticed that this JMX agent was taking a significant amount of CPU time, and which was affecting our Kafka performance. So I wrote a small fix which minimized the amount of scraping you need to do. This fix is now in the open source world as well by another contributor, so thank you for that. That is relevant to you. And we saw a dramatic decrease in CPU usage. We basically reduced our CPU usage by half for this particular Kafka cluster. And that was a net benefit because we didn't need to scale up this Kafka cluster any longer. These tools for profiling, like the Java Flight Recorder, now come as standard in the Java runtime from JRE 11 onwards. They just need to be enabled and exposed. Node.js, for example, has a dedicated performance team, and they are doing some fantastic work to tune performance of many underlying APIs that engineers rely on. Now, many of these improvements are non-breaking, micro tweaks that culminate into large-scale improvements. For example, reading an ASCII encoded file, which is a pretty common use case, has seen a large jump in Node 18 with added throughput. Python as well is getting a massive speed up. There's a small task force funded by the wonderful folks at Microsoft and led by the Python benevolent dictator for life, Guido van Rossum, to go and tackle some of the performance bottlenecks in Python. So with some minimal work handling deprecations, it can be as simple as upgrading your Python runtime to 3.11 and taking advantage of some of these speed improvements in production. You don't need to go and change your entire programming toolchain. You don't need to go and rewrite all of your systems. But being able to keep on top of your toolchain can still yield these massive improvements in the software that you run. Now, earlier on, I talked about Java Flight Recorder and mission control. So, for example, at Monzo, all of our systems are written in Go. And within Go, you can expose a profiling server that allows you to grab profiles of running systems. Now, from day one, we've had this enabled in our production cluster, and the profiling tool allows you to grab these profiles with no impact, well, with very minimal impact on latency of running applications. And we've exposed this to all of our engineers to be able to access. So any engineer that is curious can go in and grab a profile. And there is no memory data that is leaked into the profile. It's a really, really cool piece of software. And this is a great capability, for example, during incidents where we have a system using more resources than we think or that we assume it should be serving for the number of requests it's serving. It's also really great. We have a channel on our Slack channel called Graph Trending Downwards, and it's where engineers can take profiles of systems and make an improvement with the code and deploy it and see a decrease in CPU, which ultimately means we reduce our costs. Now, that last bit is really, really important. We've developed a gut intuition based on our practices and how much performance we should expect. It's not an exact science, but typically a service can service tens of thousands of requests per CPU core that is allocated. So if you're running a service which can only service 10 requests per CPU core, it's definitely worth probing into that. If you have an existing application where you can't add profiling tools, maybe because it's closed source or you don't want to go and modify the source code and figure out how it is built, you can still gain some insights through BPF and eBPF tools, which can leverage kernel-based tracing, assuming that you're on Linux 4.1 or above. Now, my favorite tool chain in this toolbox continues to be BPF trace. I like to use it even alongside the language-specific profiling tools because it gives a really good insight into the file system and networking stack via syscall tracking. Now, all of the tools and arrows are things that can be probed within your system. So there is really no excuse to get deeper into the hardware and get better understanding of the hardware. You can download, all of these tools are open source that you can grab and modify. And there is not a lot of operational overhead to running these things in production, assuming that you have access to the system that is underlying. And if not, then have your operations folks give you exposure to these tools because they're not going to affect your runtime performance and they're not going to leak any data. With shifts in both hardware and software, there's a cultural shift in writing and sometimes rewriting core software to take better advantage of the hardware. And we can all play a part in that by evaluating our systems, profiling our systems, understanding the benefits of the hardware that we're running behind, understanding the power that is available to us in modern computing. We can all have an element of mechanical sympathy. It can start with profiling and optimizing bottlenecks, making sure that you are taking full advantage of enhancements in your particular programming language. Make sure that your code is not creating tons and tons of garbage. Making sure that your kernels are updated so that you have access to new APIs like IOUing, and making sure that you are tuning and upgrading your system over time. Now, throughout this entire presentation, apart from the can with the Tim Tams, I've resisted talking about AI. And I'm not going to go deep now. It's too late in the day for that. But we're at a turning point where generative AI has captured the minds of the masses. But one big debate in the industry is the sheer amount of compute power that is required to train and operate these models. And there's low-hanging fruit in this space too. Llama, for example, is a model by the folks at Meta, and there was a popular open source implementation. And there was an excellent pull request a couple months back that tweaked the file format to take advantage of mmap, which led to a 100x improvement in load times and half as much memory used at runtime. So old tricks like mmap has been known for many decades, and memory alignment can still yield massive benefits, even in systems that we are writing today that are supposedly running the next generation of user interaction and computing. Now, here is a little bit of a hot take, so please don't mob me, especially at this hour. Most of the systems we build are glorified data processors. We take some data from one end, we translate it, and we put that data somewhere else ad infinitum. And there is low-hanging fruit even at that transformation layer too. Chances are that many of us work with JSON on a daily basis. Take a profile of your systems, and chances are there's a large portion of cumulative compute within your systems that is just serialization and deserialization. And even in the world of JSON parsers, they are getting a fine-tuning under a magnifying glass. There's a particular project that I've been interested in called SimDJSON, which uses processor instructions that are available in processors that have been running for multiple decades, single instruction, multiple data. And there's an open source C++ library, and there's bindings in many, many programming languages. You can install this, and you can parse JSON at gigabytes per second. So there are optimizations opportunities at every layer, and many layers that we work with on a daily basis. Let's go back to the statement at the beginning of my talk. Many of the systems we rely on are built for an era where hardware was quite different. The bottleneck a decade ago was present in hard drives and main memory and the networking stack and things like that. But today, hardware has gotten so fast, the bottleneck is firmly in how quickly we can execute with our software. It's staring us right in the face. In many of our organizations, we often put up faux barriers, faux guardrails that stop us from taking advantage of these hardware improvements. This room is full of smart leaders and architects, and we have a perfect chance to influence changes in culture within our organizations. These improvements are in long-term support and are in release versions. So there's very little reason to be stuck on old versions of Java. You can convince your security teams, you're missing out on many months of security, many years of security patches. You don't need to be stuck on older versions of Python. Organizations like Amazon and Microsoft are using programming languages like Rust for critical infrastructure. There's no reason why you can't use it for your companies. What we've also seen is that there are tools out there that allows our software to keep up with pace. There are features being introduced at the kernel level and within programming languages and programming paradigms and libraries which we can take advantage of simply by upgrading or changing the way that we write software. By keeping pace, we can use less compute power, less energy, less resources for the same level of output. Conversely, we can build and empower richer systems by taking full advantage of the hardware that is available to us today. And with that, thank you so much for listening.